Hello everyone and welcome to TMU Simplified Chapter 4, and the name of the chapter is Exponential and Logarithmic Function. Again, very important chapter. You get 3 to 4 questions based on exponential and logarithmic functions directly or indirectly in both the papers combined. Right. So let's move on to exponential function. Now, what is an exponential function? Exponential function is basically defined as y is equal to fx is equal to a to the power x. Now, here the difference is in most of the algebraic function, we have power of a variable, which is a constant. Here, a constant has a power which is a variable, which is x. So that's the difference. So that's how we represent a exponential function. Now, a can be, first of all, a has to be greater than 0 for it to be exponential function. A has to be greater than 0. So either and a should not be 1. A should not be 1 for a function, right? A should not be 1. 1 to the power anything is 1. So that's why when we follow the definitions of function, so that is where we say a cannot be 1, right? So these are the constraints that we have. So if we look at a, so a will either be between 0 or 1, or a will be greater than 0. So this is these are the two cases where we can get an exponential function. Now x is a variable, x can be any real number. X can be any real number, right? So I can find the value of a to the power negative, 0 as well as positive. But exponential value cannot be negative for these constraints. For these constraints, we cannot have the value of exponent as negative. So I will say the value of y will be greater than 0. The value of y is the function value and y is the value of a to the power x. So a to the power x under these constraints for it to be a function, right, cannot be negative or 0. So if I look at the graph of y equal to a to the power x, so if a is greater than 0, the graph of this would look like this, right? So this is how it looks like. It goes like this. So it is, the shape is like this. So for negative values, for x being negative, it will become very small, almost approaching 0 but not 0. So it can't be 0 and negative. And if I know that any number to the power 0 is 1, so if I put x as 0, which is on the y-axis, I'll get the value of y as 1. So I can say this point is 0 comma 1, right? Here, sorry, I'm taking a as greater than 1, right? Just a correction, a is greater than 1. For a greater than 1, this is how the graph looks like, right? On the contrary, if a is between 0 and 1, the graph would be the other way around. It's like this, right? So y equal to a to the power x. The function remains the same, but the base of the exponent is now between 0 and 1. So the nature swaps, right? So that is how the exponential function looks like. Like for example, suppose I say y equal to 2 to the power x. So if I plot them also, I can very well figure it out, the graph. Like at x equal to 0, y will be 1. So this is this point. At x equal to 1, y will be 2. So at 1 it is 2. Right. At x equal to say 2, y is 4. So at 2 it becomes 4. So it's like this. At x equal to minus 1, y will be 2 to the power minus 1, which is half. So at minus 1 it will be half. At minus 2 it will be 2 to the power minus 2, which is 1 by 4. So the value when x is negative will always lie between 0 and 1. So you can see it, if I connect all the points, so the shape will be like this. So this is how an exponential function looks like. So it will not be touching the x-axis, it will become parallel, almost parallel to x-axis towards the end. So it will be approaching 0, but will not be 0. Right? So this is how it looks like. And on the contrary, if I have a graph of y equal to, say, half to the power x. So I know, same graph if I draw, if I take x as 0, it will be 0 only. Half to the power 0 will also be 0. So x 0, y will be 1. At x equal to 1 now, y will be half. So x equal to 1, y will be half somewhere here. And x equal to 2, y will be 1 by 4. So somewhere here, right? And at x equal to, say, minus 1. So half to the power minus 1 will give me 1, 2 to the power minus 1, which is 2. So it will be 2. So the graph looks like this, right? Almost parallel. So you can see that the graph will be similar, but it will be opposite in nature. So these are the graphs of exponents which you need to remember. Very, very important. There have been a lot of questions in TMUA which are based on exponential graph, especially in the reasoning part also sometimes, reasoning section, the second paper, knowing these graphs becomes very, very important. So you should know all of them. Now, we also use y is equal to e to the power x. Now, e is an irrational number which has a value 2.7 something and so on. So this is called an exponent, right? So it's a specific value of e that we of the base of an exponent that we use. So sometimes you'll come across. So now this the base is greater than 1, so the graph will be right like this, of e to the power x. So e to the power x has a fixed graph because the value of e is more than 1. The graph will take this shape only, of similar to a graph which is where the exponent, the base of the exponent is greater than 1. Right. Now for different things, like if I say we have y equal to 2 to the power x, y equal to 3 to the power x, y equal to 4 to the power x, how the graph will be, they will all be similar, but there will be few things, nuances here and there which you have to remember. I know that 2 to the power 1 will be 2 and 3 to the power 1 will be 3, but at x equal to 0, all of them will be 1. So it will be 0. So at 0 it will be 1. But for, in case of 2 to the power x, at 1, x equal to 1, the value will be 2. But for the other graph, it will be 3. Right? So if the graph looks like this for 2 to the power x, so it will look like this for 3 to the power x, slightly below. So this is the graph of y equal to 2 to the power x. So this is the graph of y equal to 3 to the power x. So these differences you should know how to create, right? So the graph will be slightly, the on the negative side will be below 2 to the power x. The graph of 3 to the power x will be above on the right hand side, that is when x is positive, and will be below when x is negative. So for negative values, it will give me smaller values, and for yes, positive values, it will give me higher values. So this is something which we have to understand, right? Because 2 to the power minus 1 is half, and 3 to the power minus 1 is 1 by 3. So for negative value, it will give me a smaller value, and for positive, it will give me a bigger value. So this is how you can create a difference between the graphs, right? Same graph, same shape, but the position will be a little different. So that is something which one should know while tackling questions on exponential functions. So these are the things which are very, very important for one to know while doing questions on exponents, right? Now then there comes the properties of exponents. Properties of exponents, right? Very simple property. If I say a to the power b into a to the power c will give me a to the power b plus c. It's very simple, no? It's not a property even. If I say 2 cube into 2 square, so I'm multiplying 2 3 times and 2 times, so it gives me 2 to the power 5. Right? So that's why the power gets added, 3 plus 2, 5. So it's not a property, it's simple observations, right? But yes, they are taught us in a manner which says it's a property, right? So if a to the power b is divided by a to the power c, so a to the power b minus c. Same logic. Any number to the power 0 is 1, that we have already covered, right? That is something which you need to know. Then a to the power b to the power c can be written as a to the power bc. I'm just going through them quickly because this is something which we have been doing for a long time. So it's not something new to you. So, right, a to the power c to the power b, right? So these are some of the properties. Then if we have root of a, this can be written as a to the power half. If we have cube root of a, then it can be written as a to the power 1 by 3. Similarly, if we have nth root of a, so it will be a to the power 1 by n. So for roots, exponents, right, we have to put it like this. Similarly, if we have a negative power like a to the power minus n, so it becomes 1 upon a to the power n. Okay. So then if we come across something like a to the power b is c, and I have to find the value of a, so a becomes c to the power 1 by b, right? This is the operation that we perform. Like for example, if I say a square is 4, so a is equal to plus minus root of 4, which will be plus minus 2. So this is something which is again very common, but yeah, and most of us know this already. Then comes, like, if I say then another thing, like if I say a to the power b is equal to a to the power c. So most of us deduce that b is equal to c. Since the bases are same, so powers need to be same. I just wanted to tell you one more thing, or you should think that can they still be equal without b being equal to c? Yes. So the only exception is if a is 1. If a is 1, then b may not be equal to, right, they can still be equal, like 1 to the power 7 equal to 1 to the power 7, but if they are not equal, then also 1 to the power 6 is equal to 1 to the power 7. 1 to the power anything will be 1 itself. So considering that, this can be tackled very, very easily, right? So these kind of, especially when we, when we are doing when we're doing paper 2 and we have questions on proofs, identifying the error in the proofs, and so on and so forth. These kind of things becomes very, very important, right? Because these are the you know these are the basics that they test you on, right? So let's see one more. If I say m to the power p is equal to n to the power p, now here the powers are same, so it implies that m is equal to n, which is correct. But is there an exception? Yes. So if p is 0, then m may not be equal to n. Any number to the power 0 is 1. So if m is 7 and n is all 8, so 7 to the power 0 equal to 8 to the power 0, because both will be 1. So this is something which is worth remembering. Why? Because these are, as I've told you, right, these are something, this can be exploited especially in paper 2, where we have to identify the error in the proof, right? So let's look at some questions now. What type of questions can be asked? Although I've compiled a lot of questions at the end of the book in the exercise, but these are some of the examples I'm doing with you. So suppose we come across this. So I know any number to the power 0 is 1. So I can simply put x square minus 5x plus 6 is equal to 0. Then only it will be 1. And this will give me two roots, 2 or 3. So these are the values of x. Very simple, But yes, just one observation that we have to make. Now, these type of questions, wherever we have, we do it by taking the lower value common. So I know 5 to among 5 to the power x plus 1 and 5 to the power x minus 1, the smaller value is 5 to the power x minus 1. So if I take this as common, so I need to know if I have 5 to the power x plus 1 here, so what needs to be done so that if I've taken 5 to the power x minus 1 common, so what will I left with? So I need to think, what should I add to x minus 1 so that it becomes x plus 1? So I simply, automatically it will come to, in my head, that will be 2. So I'm left with 5 square minus 1 equal to 24. So this gives me 5 to the power x minus 1 into 24 equal to 24. And this cancels. Now 5 to the power x minus 1 is 1, and that is only possible when x minus 1 is 0. So x is 1. Right? So this is how we can solve these kind of problems. Not very difficult, but yes, the level can increase in TMUA, which and such level problems have compiled towards the end. Do them. Right. Next. Again, looks little intimidating, but it's not. If we follow the same process, so here I can take 6 to the power x common, so I'm left with 1 plus 6 to the power 1, and if I take 2 to the power x common, and I am left with 1 plus 2 to the power 1 plus 2 square. So this gives me 6 to the power x into 7, and this gives me 2 to the power x into 7. 4 plus 2 plus 1. This gets cancelled. Now you must be wondering, how is this possible that 6 to the power x is equal to 2 to the power x? So some of you may believe that there is no solution to it. Although there is one solution to it, as I told you, if x becomes 0, then both of them will become 1 and they are equal. So there is one solution to it, which is x equal to 0. Right? So these are things which you need to remember in exponential function. Right. Now let's move on to the next function, and that is logarithmic function. Now, logs we have done so many times, but logarithmic function, why is it there? First of all, we have to understand. Now, if I have a to the power b is equal to c, an exponential form, so see, I can also make a the subject. A will be c to the power 1 by b, right? This is also exponential form. But if I express need to express b in terms of a and c, then what do I do? That is where the mathematician thought, how can we do that? And they introduced a function called log. So I can say the same exponential form can be written as by introducing a new function. They're just connecting b, or they're expressing b in terms of a and c. So b expressed in terms of a and c will be log of c in base a. So the power will be here. I'll take log of c and I'll put the base of the exponent as the base of a log. Now this is a single entity. There is a number whose log I am taking and in a particular base which I am taking. So log of c in base a. So I read this as log of c in base a. So this is something which you have to understand. Very, very important. Right? So this is how we change our exponential form to log form and log form to exponential form. Like for example, suppose we have log z a equal to y. So how will I change it to exponential form? Now I know this should have been a power, this should be the base of the exponent, and log will vanish. So z will become a to the power y. This is important essentially. Why? Because you will often have to convert a log form into exponential form or an exponential form into log form. So very, very important aspect of log. And there's see, when I write it as a function, so that it has another meaning to it, right? Like Suppose I say y equal to a to the power x is exponential function. Now we know that if I have to express x as a function of y, so it gives me x equal to, just a minute, x equal to log y base a. Now, all those who have studied calculus, which you have, you must be knowing in chapter functions, there is something called inverse of a function. So, how do we do that? Once I've expressed x in terms of y and I replace y by x and x by y, so I get this log. So, it's a very, very interesting case that the log function is an inverse of exponential function and vice versa. It's a very important, thing to remember, that the logarithmic function is also inverse of an exponential function. So if we have an exponential function, then the inverse of that will be logarithmic function, because the process to find inverse function, fits in here. So inverse of a function of an exponential function is a logarithmic function. Very, very important. Now, what do we mean by inverse of a function? So inverse of a function you must have studied graphically. We know how to calculate. Yes, of course, I just told you. Inverse of a function graphically means image of a function in the line y equal to x, y equal to x. So if I draw the graph of logarithm of exponential function, which I know for a greater than or 1 is this, and if I draw a line y equal to x like this, so if I have to find the logarithmic function, right, logarithmic function of this, uh, let me, I've done little mistake, let me just correct it. Okay, y equal to x, so x0 y is 1, at x equal to 1, x equal to, just a minute, just a minute. Y equal to x is this line, and my exponential function is like this, and my logarithmic function therefore has to be the reflection in the line y equal to x. So it will be like this. So you can see for a greater than 1, this is the graph. So I am just using a different color for it. So if I draw it by the red graph, so red graph gives me the graph of the logarithmic function. So this is, as you can see, that the logarithmic graph is the reflection of the exponential graph in the line y equal to x. So it's so it's inverse of it, right? So knowing all these things, helps. Especially, I told you, whenever reasoning based questions are there, contrapositives, necessary and sufficient conditions, all those kind of stuff which is there in the second paper. So understanding of graphs and functions is very, very important. It's of immense value, right? So this you have understood. Now let's move on to the graph itself. So if I say we have y is equal to, just a minute, okay. So if I say y is equal to fx equal to log of x in base a, so here also there are certain constraints. X should be greater than 0. Log of 0 and negative numbers is not defined. A should also be greater than 0 and A should not be 1. So you can see, and Y should be any real number. So, and just the way it happens in the inverse function, you can see it's happened here also. For exponential function, the domain was any real number, the values of x was any real number, y was greater than 0, and here it has swapped the nature, which happens in the case of inverse functions, right? So these are the characteristics which you need to follow. We can see the constraints or characteristics. So x is greater than 0, a is greater than 0, but a cannot be 1, and y is any real numbers. But since again we have two cases, if a is greater than 1, then the graph looks like this, as I have told you. It looks like this, right? So here this is 1 comma 0. Log of 1 in any base is 0 simply because a to the power 0 is 1. So using the same exponential form, I can verify that log of 1 in any base is 0, right? But if a lies between 0 and 1, then the graph will be the other way around. Like in case of exponent also, it becomes other way around. So this also becomes other way around. This will still be 1 comma 0. So these are the graph of logarithmic functions which you have to remember, and exponential functions. So these are very important things which I'm telling you, which you should remember, because this helps you in understanding the questions much better when it comes to the second paper especially, right? So let's now discuss the properties of log. So properties of log starts with log of a number in the same base is always 1. Just to verify, if I use a to the power 1 is a, right? So if I change it to exponential form, so it gets verified very well. Then log of a in some base c plus log of b in some base c. Property will only be applied when bases are same. So it becomes log of ab in base c. So if you have a lot of log values with same base and you're adding them, so it converts to the single log, right, with the same base, but the numbers will get multiplied, right? Then if I have log, see, all these we have done. So I'm not investing a lot of time on properties. I'm just going through them. Why? Because this is a part and parcel of something which we have done in school, right? So a to the power c minus b to the power c will be log of a by b in base c. So if it's minus, then obviously it gets divided. Also, if we have log minus log b in base c, so it is nothing minus, if you have a log value, so I can say it's log 1 by b in base c, right? So simple to understand. If I put a 0, so I can write, I told you log 1 in any base is 0. So I can write it as log 1 in base c minus log b in base c. And if I now apply this property, so it gives me log 1 by b, right? So using this, I can form this property. Okay. Then if we have log a to the power m and base c to the power n, now this can be written as, so m, this m will go here, and this n of the base goes in the reciprocal. So it comes here, right? It comes here, right? So m by n log a base c. This is another property worth remembering, right? Then if we have log a in base c, now this can be written as log a in some other base m upon log c in some other base m. Change of base is happening. So this is called change of base property, right? So we can write log a in base c as log a with some other base m upon log c with some other, with the same base m. So I can introduce a base myself as it is required in the problem, right? Again, mind you, all these properties are very important for proof questions in the second paper, right? So knowing them properly is something which is very important. Now, log a to the base b, always remember, if I reciprocate a log, then the number and the base interchanges. So it's reciprocal, right? So on reciprocation of a log, the number and its base interchanges. Then we have a property, if we have a to the power log b in base a. Now it's exponent log property. We have an exponent, but in the power of the exponent we have log, and the base of the exponent and the base of the log are same, then it is same as b. Very important property which one should remember. So these are some of the properties of logs which we need to remember, right? Now let's move on to, okay, few more things, just one or two more things. If I say log in base a base b is equal to log of say c in base b. Now since log, you saw the graph, and we saw the graph, it's a one-to-one function. So if it's one-to-one function, so I can say that a is equal to c. So for two different values of say x, the log value cannot be same. So if log of a in base b is equal to log of c in base b, then a is equal to c, right? It's something which you should remember. But if we talk about inequality, especially the log ones, so if I have log in a in base c greater than log b in base c, now here comes the graph part. Many of you may tend to think that a will be greater than b, but a is greater than b if the graph is increasing. So if I have a graph like this, which is an increasing log, it's an increasing function, right? As x is increasing, y is also increasing. But this is specifically when c is greater than 1, the base is greater than 1. Then I will say a is greater than b. But if I have the other graph which is decreasing, as x is increasing, y is diminishing. So log a greater than c greater than log b greater than c, and here since c lies between 0 and 1, so I will say a is less than b, since it's a decreasing function, right? So this is something which you will study in calculus. You must have studied in calculus, but if not, then I'll cover it later in the chapters, right? So right now just understand this much, right? Okay. Now let's do few problems of logs which are similar to what we can expect in TMUA. Now this is log, there are many logs, right? So the outermost log. Now when we have such logarithmic equations, so it's better that we change it to exponential forms. So I know if I have to change it to exponential form, so 3 will go here and 2 will go in the power. So I'll be left with 5 plus 4 log base 3x minus 1 is equal to 3 to the power 2, which will give me 4 log 3 x to the minus 1, x minus 1, sorry, 9 minus 5 is 4. And this probably will give me this as 4 divided by 4 is 1. Now again, if I change it to the exponential form, so this goes here, so I get 3 is equal to x minus 1. Now x is 4. X is 4. But since I need to know that since I know that log of 0 and negative number is not defined, so whatever answer I've got, I need to verify first of all. First of all, I have to verify this log. If I put 4 here, it will be 3, so log of which exists. Now log 3 in base 3, as I told you, the first property will give me 1. So it becomes 5 plus 4, and 5 plus 4 is 9, which is a positive number. So this is a valid answer. At any point of time, suppose I was solving and I got x as say 0, then if I put it here, or 1, if I take x as 1, that's not the right answer, because if I put 1 here, then 1 minus 1 becomes 0, and log of 0 is not defined. So you need to be very careful while solving that the answer should be consistent with the constraint or the characteristics of log, right? Very important, especially again, as I told you, paper 2, proof part, very important. Right, now there comes the next question. Now this is log a plus log b, which I can apply a property log a into b, log base 2, 3 minus x into 1 minus x is equal to 3. Now if I change it to the logarithmic form, so I will be getting 3 minus 3x minus x plus x square is equal to 2 to the power 3. Now I'll get x square minus 4x and 3 minus 8 is minus 5 equal to 0. Now this will give me the two values of x. One of them is 5 and the other is minus 1. But I cannot take 5, because if I put a 5 here, then the logs will become negative. The number of which I am taking log of will become negative. So 5 is not allowed. If I put minus 1, so 3 minus minus 1 will become 4, perfectly all right, and 1 minus minus 1 will become 2, which is perfectly all right. So the answer will only be minus 1. 5 will be discarded. Very, very important. Very, very important, right? Let's move on to the next. Now, if I use the property, last property which I have told you, so this will be log base 2, 9 to the 9 minus 2 to the power x will be 3 minus x. As I told you, a is b only, right? So same thing, these two are same, it will be 3 minus x. Now if I change it to the exponential form, so I'm gonna get 9 minus 2 to the power x equal to 2 3 minus x. So this is what I have got. Now this will give me 9 minus 2 to the power x equal to a 2 to the power 3 upon 2 to the power x, right? So this will give me 9 into 2 to the power x minus 2 to the power 2x equal to 8. Now this becomes a quadratic, right? As I've told you in the first chapter, this is equation reducible to quadratic. So if I put 2 to the power x as t, then 2 to the power 2x becomes t squared, which I've covered in the first chapter. So this will give me, it's give me t square minus 9t plus 8 equal to 0. Now this will give me two values of t, which are 8 and 1. Now, but I have to find the value of x. So 2 to the power x is 8, t is 2 to the power x, and 2 to the power x is 1. So x will be 3 or x will be 0. So these are the two values which I have got. But let's understand, can I take 3? No, because 3 minus 3 will be 0. So this is something which I cannot take. So only possible answer will be 0. So if I put x as 0, let me check. Does it verify? Yes. Yes. So answer is only x equal to 0. Very, very important, you know, for you to realize that answers are, just calculating answers is not sufficient. You need to, in logs and all, you need to verify with them with the characteristics. So if I take x as 3, so 3 minus 3, since it is becoming 0, and log of 0 and negative number is not defined, so I cannot be taking this as an answer. Okay, let's move on to the last now. So it says that x plus 1 to the power log base 10 x plus 1 is equal to 100 times x plus 1. So this is what I have obtained. Now, here, how would I want to go about, right, is the question. Now, if you look at this and I send it here, so x plus 1 to the power log base 10 x plus 1 upon x plus 1 is equal to 100, right? This is what I have got. So it gives me, right, just a minute. It gives me x plus 1 to the power log base 10 x plus 1 minus 1 is equal to 100. Now, if I take log of both sides with log base 10, so it might just be very helpful. So if I take log of both sides with base 10, since base is 10 here, so I'll be getting log base 10 x plus 1 to the power log base 10 x plus 1 minus 1 is equal to log base 10 100. Now this will further give me log base 10 x plus 1. I am applying the property of log a to the power m is m log a minus 1, right, times log base 10 x plus 1 is equal to, now this can be written as 10 square and 2 will go here, so this becomes 2, which most of us know. Now let's put log, again substitution slightly I'm doing so that it becomes easy, as t. It becomes t minus 1 into t is equal to 2. This is again a quadratic. T square minus t minus 2 equal to 0. And this will give me value of t as 2 or minus 1. So now I have log base 10 x plus 1 is either 2 or log 10 x plus 1 is either minus 1. So I will be getting, if I change it to exponential form, x plus 1 is 10 square or x plus 1 is 10 to the power minus 1. So x will either be 99 or x will be 1 by 10 minus 1, which is minus 9 by 10. So these are the two values I am getting. But let us verify, are these values accountable? So if I put 99, yeah, so yeah, perfectly all right, 99 I can take. But can I take it as minus 9 by 10? So if I put minus 9 by 10, so minus 9 by 10 plus 1 will be 1 by 10, which is also positive. So there is no way I can reject any of them, because I am taking log of x, this is brackets x plus 1. So if I am taking this, then I think it doesn't matter, because both this will be 1 by 10. So I am getting yeah, 1 by 10. Yes, absolutely. So both are valid. Both are valid. So these are some of the examples which are there in logarithms. So I will come up with the, there are, towards the end of the chapter, there are questions which I've compiled. So I'll come up with the video solution of this later on, right? So till then, take care. Have a nice day.